Okay, so we're going to take a look at the integrated rate law. Remember, the regular rate law, normal rate law, or differential rate law, whatever you want to call it, shows us how the rate of reaction changes when you change the concentration of reactants. The integrated rate law talks about how concentration of these reactants vary over time. Now, they're related, but they're used a little bit differently. Okay? For now, we're only going to deal with reactions that have one reactant. So a decomposition, essentially. Things get a little bit more complex when you have more than one reactant. We'll talk about pseudo first order rate laws in a bit. Okay, so we're going to start with the first order integrated rate law. Here's one way to write it. That's the natural log of the concentration of substance A at some time is equal to negative K, K is our rate law constant, plus the natural log of the initial concentration of A. So concentration A naught with a little zero subscripted, that's the initial concentration of A, what it started with. And concentration A without that little zero is the concentration at time t, whatever t happens to be, however many seconds into the reaction we are. Okay? That means using that we can calculate the concentration of that particular reactant at any time along this of this reaction. Now this is for first order reactions only. First order in A and first order overall. Remember, there's only one reactant, A, so if it's first order in A, then the whole order of the whole reaction is A. We can graphically figure this out too. So you can figure out the first order integrated rate law by taking some data and plotting it correctly. Okay? If you use this in this form, natural log of concentration A equals negative KT plus natural log of A naught, then we can put it, that's y equals mx plus b form, where y is the natural log of A, x is t, and the slope is negative k. Okay, and then the place where it crosses the y-axis is the initial concentration of A. So if you set up a graph where you have the y-axis equal to the natural log of the concentration of your reactant, and the x-axis is time, and you plot those natural logs of the concentrations that you've measured, you should get a straight line if it's first order. No other order will give you a straight line if you plot natural log of concentration on the y-axis and time on the x-axis. You'll only get a straight line if it's first order, and that's because of the equation. Okay? Now, we have this concept called half-life. Okay? Half-life is the time it takes for a reactant's concentration to reach half of its original value. All right? So the time it takes to use up half of what you started with, which is what half-life is, especially when we're talking about nuclear decay. By the way, you may remember back when we first talked about nuclear decay that I told you that nuclear decay reactions were always first order. This is why. This is what it means. Okay? So for first order reactions, the half-life doesn't depend on the concentration that you start with. Now, I need to kind of show you where this comes from, and so that you can understand why concentration is not involved, and this and that. Okay? So let's take a look at a quick calculation to kind of figure out where half-life comes from. Okay, so T1/2, that's our half-life. That's what we're going to call half-life. Okay, and remember, that's the amount of time necessary for half the concentration of our reactant to decrease to half of what it used to be. If we take the first order rate equation that we just saw, which was natural log of concentration of A is equal to negative K times T plus the natural log of the initial concentration of A, and that's y equals mx plus b. Right? I'm going to rearrange this a little bit. Okay, I'm going to do a little bit of algebra, and I'll show you the algebra a little bit later on, but basically I can rearrange this to natural log of concentration A naught over concentration A is equal to KT. Okay, if I understand that at the half-life, at T1/2, the concentration of A is equal to half of the concentration of A naught. That's the definition of half-life. The concentration is half of what it was when you started. Okay? I can plug in then this expression, okay, half A naught for A in here. And I get natural log of A naught over a half A naught is equal to k times t. Right? Well, the natural log of a naught over half a naught is the same as the natural log of, well, these cancel out to 1s, 1 over 1/2, which is just the natural log of 2. And that's equal to kt. Okay? So the natural log of 2 is equal to k times t. T 1/2 we're at now, right? Natural log of 2 is 0.693, and that's equal to k times t 1/2. And so solving for t 1/2, I get t 1/2 is equal to 0.693 over k. Okay? So that's where I get the formula for half-life. What's interesting, though, if you notice, in the formula for half-life, there is no concentration term. So what we mean by this does not depend on concentration is that the half-life, it doesn't matter how much you start with, the half-life is going to be the same, regardless of how much stuff you start with. Now, you might say, well, that doesn't sound right. Seems like if you start with more, it should take longer to get there, right? It should take longer to decrease it to half. But with a first-order reaction, the fact is, the more you start with, remember what the rate law expression is for first order. Rate is equal to k times a, concentration of A, which means if I double the concentration of A, what happens to the rate? It doubles. The greater the concentration in first order, the faster the reaction goes. So the more you have, the faster the reaction will go so that it doesn't take any more time to get to the half-life. Okay? That's why, for first order reactions, that's why concentration is not a factor when figuring out the half-life, the amount of time it takes. The more you have to start with, the faster it goes to get there. Understand? Second order. Now this is second order in A and second order overall. This would be what it would look like. 1 over A is equal to kt plus 1 over A naught. So I put this again in y equals mx plus b form, okay, where y is 1 over A concentration A, x is still time, and the intercept is 1 over the initial concentration of A, okay? And if we plot 1 over A concentration versus T, we get a straight line. Now notice, this is data for a second order reaction. On the left here is a graph of the way we graph the first order. Natural log of concentration versus time, we don't get a straight line. If you graph the natural log of concentration versus time and you don't get a straight line, it's not first order. But if we then graph 1 over the concentration versus time, we get a straight line. Now I know it's second order. We can do the same thing, and you can do the substitution like the calculation I just showed you to figure out the half-life, to sort of algebraically figure out the half-life, but I've got it here for you. Okay? Half-life does depend on the concentration here, but look at how it depends on the concentration. T 1/2 is 1 over k times A naught. If I double the concentration of A, what happens to the half-life? It gets shorter. So this seems like the more stuff I start with, not only does the reaction go faster, but it goes faster and faster and faster the more I have. Well, that's what a second order reaction is like. Remember, our second order rate law is rate is equal to Ka squared, which means if I double the concentration of A, the rate quadruples. It goes 4 times faster instead of just doubling, which means that the greater the concentration that I start with, the less time it's going to take for me to use it up. Again, it seems counterintuitive, but if you just look at the math, that's kind of how it works. Okay, so the slope of this second order graph will be k, your k value. So all of these are determined experimentally. You can figure out not only what order it is by plotting it and figuring out what the straight line looks like, or what you have to plot to get the straight line, but then you can also then use that line, get the slope, find k, and you can come up with a good expression for the rate there. Okay. Now, we do have something called zero order. We talked a little bit about zero order reactions, and we said that if it's zero order, that means that the concentration of that reactant doesn't affect the rate at all, right? A zero order reaction, you can double the reactants concentration, and the rate stays the same. It doesn't change. Now, think about what that means in terms of half-life. Here's the expression for the integrated rate law, zero order. Concentration A is equal to negative KT plus A naught. So what am I going to plot here? If I wanted to plot to see if it's a zero order, what gives me a straight line? Well, a straight line is given by a concentration versus time. Okay, it's a straight line with a slope of negative k. So it looks like this. Now, what does that imply about half-life? Well, what it implies about half-life is that it does depend on the concentration. And look down at the bottom here. What happens if I increase the concentration of A? Well, it takes longer to get to the half-life. Why? Because a zero-order reaction, the rate is not affected by concentration. The reaction rate is constant in a zero-order reaction. Nothing you do is going to speed it up when you mess with the concentration. So the more you have, if the rate stays the same, the longer it's going to take to get to the half-life. Okay? So you've got three different ones. We don't do much more than that. We don't do third order or fourth order because the math gets much more complex. But we do have something called a pseudo first order reaction. So if you have a reaction that has more than one reactant, so for example, here's one. We've got bromate ions reacting with bromide ions in an acidic situation to form bromine and water. Okay? This has three reactants: bromate, bromide, and H+. The rate expression for this reaction looks like this. It's first order in bromate, it's first order in bromide, and it's second order in H+. That's experimentally determined. Remember, that's the only way you can determine a rate law is experimentally. When you perform this reaction, and you have two of the reactants very, very high concentrations and one very low. So, for example, if we make the concentration of bromate 0.0010 molar, the bromide and H+ are both 1 molar. They're 1,000 times bigger than the concentration of bromate. Okay? What that means is that when this reaction occurs, so little of those two reactants with the high concentrations are actually going to get used up that if you take sig figs into account, the concentrations of those two are just not going to change. They're going to stay the same, right? Because not much bromide and H+ is going to get used up if I only have 0.0010 moles per liter of bromate. We're going to have very little get used up, and there's going to be a ton left, and it's almost going to seem as if they didn't change at all. Those concentrations didn't change, okay? So the concentration of bromide at any time is basically the same as it was when you started, and same thing with H+, okay? So the rate law essentially then can be thought of as being K times bromate to the first power times bromide, the initial concentration, times H+, the initial concentration squared, okay? And if we take those second two concentrations, the bromide and the H+, and we smush it together with the original rate constant K, we get a new K value, K prime. And so we can say that the rate is K prime bromate to the first power. This is now a first order reaction. We treat it like a first order reaction. It's called pseudo first order. K prime is K times the two very high concentrations. But it simplifies things in terms of the math a little bit. Okay? And so we can calculate K prime, and then we can calculate K from that, as long as we know the initial concentrations. And so we could treat this, it's pseudo first order because we treat it like a first order mathematically, even though it has three reactants that do kind of affect it. But because those second two reactants are so high in concentration, they don't seem to change, and therefore they don't really figure in. We kind of lump it all together in our constant. So going back, and let's just take a look. We have a first order reaction. We're just going to find some information about this. So we have a half-life of 20 minutes. Okay, we want to find K for this reaction. So remember that for first order reactions, T1 half is 0.693, okay, over K. And so K is equal to 0.693 over T1 half, 0.693 over T1 half. That's all you got to do. And this is done in minutes, 1 over minutes. Okay, the K value, the units of K, for a first order reaction will be 1 over time. Now, what about the second part? How much time is required for the reaction to be 75% complete? All right, so this takes a little bit more thought. What's going on if it's 75% complete? All right, well, let's think about it. Here's our first order rate equation. Here's how I got the other version of it in the calculation that I showed you a little while ago. Okay, I'm just going to do a little bit of algebra. If natural log of concentration of A is equal to negative KT plus natural log of initial concentration, I can subtract initial concentration from both sides. I can use the rule of logs, and then I can use the inverse. And I get what I had when I showed you just a little while ago. So follow these from left down, then to right down, It's just algebra that changes one form into the other. Okay, so using that, 75% of A is consumed. That means that concentration of A is 25% what it used to be, or 0.25. Okay, so that means that we have natural log of 1 over 0.25. 1 over 0.25 is 4. Natural log of 4 is equal to KT. So natural log of 4 is 3.47 times 10 to the minus second T. T is 40 minutes. Right, that's how we use the integrated rate law. It's used to figure out how much time it's going to take for a reaction to decrease a certain amount of concentration, or what's the concentration going to be at a certain time in the reaction. And that's essentially it. Now, on the green sheet on the AP exam, you get the first and second order rate equations. I don't think they give you the zero order, and that's probably because they don't use it very much. It's usually first order that they use in problems. So watch the video a couple times, make sure you kind of understand what's basically happening here, and then work the practice problems.